Welcome to AP Calculus, Chapter 3. This is our second day on 4B. On the first day of Chapter 3, Section 4, we talked about a lot of physics definitions and some business definitions. And to be perfectly honest, most of what we're going to be doing in AP Calculus will be the physics definitions. But we will definitely have some discussion on business definition, marginal cost, marginal revenue. Okay, one thing you're going to see a whole lot of in this class is, and probably on the AP test as well, you're going to see something where it talks about a particle moves along a line. Oftentimes they'll say the x-axis so that its position at time t is greater than or equal to 0 is given by a position function. Critical to remember, we're going to see words like position, we're going to see words like velocity. Here's velocity. We're going to see words like acceleration. It's going to be really critical that we pay close attention to those. That's going to be a big key to what we're doing. We have words like position, velocity, which is the first derivative of position, and we have acceleration, which is the second derivative of position, or the first derivative of velocity. So we really have to be attuned to that. And what's going to happen, I'm certain it's going to get some of you. I remember when I was sitting in your seats, it got me. We're going to deal with position equations primarily for a while, and then all of a sudden they're going to throw in and say, well, the velocity is given as a function, and we're going to think that we're at position because we're so accustomed to just dealing with that, whereas what they've really given us is the derivative of position when they give velocity. So we'll have to be really alert where we're starting, but we typically go from position to velocity to acceleration. And a good question right now would be, well, what if they give me velocity? How do I determine position? Stay tuned for second semester. All right. So S is measured in meters and seconds. So our position would just be meters, our velocity would be meters per second, and our acceleration would be meters per second squared. So first it says find the displacement. For displacement, I kind of like to think of a bathtub that's draining slowly while water's coming in, and displacement is basically how much the water rises or falls over some time period. Maybe in this case, so I guess what I'm saying is I might put a whole lot of water in there, enough water to fill it 6 inches higher, but maybe it only fills it an inch higher, or maybe after time it's an inch lower. When we're thinking about a particle moving along a line, if I make that similar to the x-axis here, maybe we start here and then we move to this point and then we move back to here and then we move over there and then we move back to here. I've really only displaced that far. So all I need for my displacement is my position at time 0 and my position at time 5. So my position at time 0 is 0 squared minus 3 times 0 plus 2, or 2. What are we dealing in? Meters. And at S5, I'm 5 squared minus 3 times 5 plus 2, or 25 minus 15, 10 plus 2, 12 meters. So my displacement is 12 minus 2, or 10 meters. Not necessarily sure where I was after 1, 2, 3, 4 seconds, but after 5 seconds, I was 10 meters from where I started. Might have gotten farther than that along the way. Okay, find the average velocity. So let's jump back to here. Our average velocity of an object can be found by distance over time. This is our change of our distance. So this is our distance to the right, or as time progresses forward, time changes, minus our initial position, divided by the change of time. So once again, velocity if I was finding an instantaneous velocity, yes, I'd want the first derivative. But for velocity, I just need where I ended up, the position. F is a position function here. I need my ending position minus my original position divided by my time. So find the average velocity. Velocity would equal, I started at 12, I ended at 12 after 5 seconds. I started at 2, and that happened over 5 seconds, so that is 2, but this is critical. We have to label this correctly. That's 10 divided by 5, 2. Our velocity is going to be in meters per second. That is critical. Now for instantaneous velocity, velocity is going to equal, we'll call it v of t, that's going to equal s prime of t, or the first derivative of our position function. Why we use s for position is a mystery to me, but that is what we often or always use. So that's an easy enough derivative, as we can see. It's just a power rule over a polynomial. We get 2t minus 3. So v of t is 2t minus 3. Therefore, we want velocity at time 4, and our velocity at time 4 then is 2 times 4, 8, minus 3, 5. It's a velocity meters per second. Find the acceleration of the particle. Well, our acceleration equals velocity's first derivative. Velocity's first derivative, velocity is 2t minus 3. Velocity's first derivative is just 2. So our acceleration at time t is 2 meters per second squared. So interesting there. If we go back here and we think about it, won't a parabola then, if we take the second derivative of a polynomial, and each time we take a derivative of a polynomial, the power reduces by 1, the second derivative of a parabola or a quadratic will always just be a constant. It has constant acceleration. You may say, well, that doesn't make much sense, because what if the parabola looks like this? We've got to start to learn to think in terms of acceleration. It's like, wait a minute, it's going down and then up. Doesn't it have negative acceleration? Acceleration is identified, whether it's positive or negative, by cupping. In other words, that is cupping up. This is actually cupping down. This is decreased acceleration by cupping. I always just kind of cup my hand. It'll be hard to show here. But this thing is cupping up. This is accelerating. In other words, my velocity, my slope here, is less than my slope at this point. My slope here is greater than my slope here. So this is decelerating, cupping down. So anyway, quadratics always have a constant acceleration. At what value of t does the particle change direction? So now we have to interpret. When does it changing directions? Is it changing directions based on where it is, its position, based on its speed at a certain time, or based on its acceleration? Well, I would be really interested in this when the velocity switches from positive to negative, is when it's changing directions. So let's take a look at its velocity. We want to set the velocity of t equal to 0, or our velocity, we've got that guy up here, 2t minus 3. We want 2t minus 3 to equal 0. That gives us t is 3/2. So if we consider that on a number line at 3/2, that's where our velocity is 0. If I put a number bigger than 3/2 into there, like 5, I get a positive. If I put a number smaller than 3/2, like 0, I get a negative. So this thing is going to the right, going to the left, but it's switching at 3/2. So the particle changes directions at 3/2. If we go back and consider our parabola, our particle is going down or to the left. See, I'm going to the right, but we're talking about a particle moving back and forth, and this is the position. So the position is getting smaller. It's moving to the left until it gets here, moving to the right. So that would be our 3/2. By the way, I had no intention of this trying to be the same parabola as that. Just an example here. So at what time does the particle change directions? At t equals 3/2 seconds. Now we need to maybe be careful there, because maybe 3/2 was just the only zero, and then we'd be positive this way and positive this way as well. So we have to kind of consider what's happening this way. We found out we were positive. What's happening before 3/2 seconds, we're negative. So we're changing our directions. Where is the particle S? Where is the particle when S is a minimum? Well, if I go back and consider my parabola, when S is a minimum, we are at our vertex. That's our position. It would be a minimum. So how can we do this? Well, we could find the x coordinate. We could find the x coordinate of the vertex of this parabola. Well, that's easy enough. Negative b on 2a. That's 3 on 2, so 3/2 again. Or we really just found it here. At what value does the particle change directions? From going down to going up, that's the velocity equation equal to 0. I think it's important to make those equations, or those connections, excuse me. So where's the particle when S is minimum? When S is minimum, again, V of t equals 0. Where is it? Well, that occurs when t equals 3/2 seconds, but where is the particle? This would be 3/2 seconds. Again, this is not really this parabola. 3/2 seconds, the particle is at this y value. So what I really want is S, the position, at 3/2. So being mechanical is going to be great. I mean, yeah, we cannot short sell the mechanics, but we're going to have to think our way through and learn to think in terms of velocity, acceleration, position. So this gives us S is a factor that takes things, squares them, subtracts 3 times them, and adds 2. So we get 9/4 minus 9/2. Something you should note on parabolas: anytime you're working with a quadratic equation like this and you put a value in here, you are going to, if it's a perfect square, this is going to be potentially, let's come back and talk about that. But it does mean something when we get this to be 9, when this is double this. But anyway, that's a discussion for another time. It doesn't really apply to this problem. I apologize. So we have 9/4 minus 18/4 plus 2, or we get negative 9/4 plus 8/4. We get negative 1/4, and that would be a really good time to grab your graphing calculator and take a look at this quadratic equation, this parabola, and make sure that our vertex is there. So what is that position? Again, we have to label our answers. Our position in this problem, in this set of problems, is meters. Okay, I'm going to stop this at this point. You can look for the next video. Will be the second page of this.